Hello, my name is Davis Binger, and let's talk about the work done draining a tank. Today we will be looking at problem 7 of the 6.7 worksheet. We will consider a water tank shaped like an inverted cone, that is an ice cream cone. The height of the cone will be 6 meters, and the base, don't be confused by the word base here, the base means the top of this cone, which has a radius of 1.5 meters. If the tank is full, how much work is required to pump the water to the top of the tank? Second, is it true that if we only fill the tank halfway up, that it takes half as much work to pump the water out of the tank? Alright, let us recall the general formula for work done draining a tank. The work is equal to the integral from a to b of rho times g times a of y times d of y dy. Now this has a lot of different mysterious constants and functions here, so let's take a moment to discuss each. A and B is the interval on which the liquid exists. So we have some tank here, and the water goes from a level here up to here. We can quantify these y values, set a scale for the tank, and assign a value A, which represents the lowest point at which water exists, and B will represent the highest point at which water exists. This interval will be the integral across which we integrate. Rho, the next term here, represents the density of the liquid. This usually is water, and we know that water has density 1,000 kilograms per cubic meter. G is the gravitational constant. We generally deal in the metric system, and we will look at gravity equal to 9.8 meters per second squared. Area as a function of y is a more complicated component to this formula. If we have a general tank, it could be any shape, but let's just consider this abstract tank here. A of y is a function which, as an input, takes a height, so the tank starts here and comes up. If we take just an arbitrary point y, that's an arbitrary height, we can take a cross section. A of y represents the area of this particular cross section. Now, d of y, we have the cross section A at the height y. D of y is the distance this particular cross section has to travel when we are draining the tank. So in this case, we have to take the cross section at a height y up to a height of 6. Our goal when solving these tank draining problems will be to identify each component, so the A, the B, the rho, the G, the A of y, and the D of y. In this case, here we have a picture of our cone. As you can see, it's a height of 6. I have decided to place the tip of the cone at the origin, so this point, which I have labeled A, is 0, 0. It goes directly up. Here's the point 0, 6, and we've defined this point C, which is 1.56. So this is make sure that the radius is equal to 1.5 meters. All right. So this is our initial setup, and we can see that if we fill the tank with water, the y values here start at 0. And there's water all through this tank. So the y values end at 6. So our range of integration will be from 0 to 6. We're dealing with water, and as I said previously, the density of water is going to be 1,000 kilograms per cubic meter. As I said previously, we will take the gravitational constant to be 9.8. And if we have a cross-section here, this represents an arbitrary cross-section at a height y. What distance will we have to lift this cross-section? We will have to lift this cross-section from here up to here. So the distance between this point, which is labeled B, and this point, which is labeled D, is 6 minus y. That gives us the function d of y. d of y is exactly 6 minus y. We have left the hardest component to identify for last, the cross-sectional area. Note that the cross-sections are all circles. The area of a circle is given by the formula pi r squared, so it's enough to identify the radius as a function of y. That is, can we find this distance? The distance from d of y to e of y is exactly this radius as a function of y. So we have two triangles. We have the triangle A, B, C, and the triangle A, D, E. Now these are similar triangles. They share the common angle at A, and the angle ADE and the angle ABC are both right. So this makes the two triangles similar, and hence we can relate the sides. Similar triangles have proportional edges. So in particular, we can relate r of y, which is the length of this edge, over y, which is the length of this edge, to the length of the edge from B to C, which is 1.5, to the length of the edge from B to A, which is 6. After simplifying this expression, we get that r of y is equal to y over 4. As the area of a circle is pi r squared, our area of our cross-section is given by the formula pi y squared over 16. Thus we have identified all of the components of our integral. We can plug these in and solve for the work. So work will be the integral from 0 to 6, 1000 times 9.8 times pi y squared over 16 times 6 minus y dy. After a bit of algebra, we can pull out all of the constants and distribute the y squared to the 6 and the negative y. The power rule allows us to integrate 6y squared to 6y cubed over 3, and allows us to integrate y cubed to y to the 4th over 4. We will evaluate this antiderivative from 0 to 6. After evaluating, our problem, our expression, simplifies to 66,150 times pi joules. So we have identified the work done to drain the tank. Let us finish the problem by looking at the second half. The second half asked us, is it true that if we only fill up the tank halfway, that it takes half as much work? Now, we have done a lot of work already. Haha, work in a work problem. Funny. We've already identified the density, the gravitational constant, the distance a cross-section travels, and the cross-sectional area. The only change in this second problem is that now we're only filling the tank halfway. That means water only exists from the base height of 0 to the halfway height, and half of 6 is 3, so it exists from 0 to 3. So the work done will be found by integrating from 0 to 3, the same expression we integrated to find the work done when the tank was full. So, as in the previous integral, we can distribute the y squared, pull out the constants, find the antiderivative, and evaluate from 0 to 3. This simplifies to 20,671.875 times pi joules. And if you take the ratio of the two answers, you see that the ratio is not 2. It's not true that if you only fill the tank up halfway, it takes half the work. And you can kind of think about this in your head a bit. Well, these components near the bottom, they're traveling a much further distance. So the work associated with a particle near the bottom will be greater. The other concession is that these cross sections near the top, they are much bigger than the cross sections near the bottom, so that there's more water traveling this short distance. So on the one hand, if you're only filling it up halfway, you're only including cross sections which are traveling further. This, you would think, would have the effect of making the work more than half. But because you are including smaller cross sections, only smaller cross sections, that has the effect of making the total work done smaller. So it's interesting to see how these things balance out. In this particular case, the work done is less than half. So you have to be, the lesson is you have to be careful with what your intuition leads you to believe. Alright, thank you for watching. As always, you can reach me by writing a comment below or emailing me at binger@math.ohio-state.edu. Thank you, and have a good evening.